Thank you very much, Giovanni, for this kind invitation, and good afternoon, ladies and gentlemen. So I'm very glad to participate to this workshop of the IEEE Magnetics Society. Certainly it would have been more enjoyable in person, but we are all facing difficult times, and these kind of online events are actually very important to continue networking and discussing about science. So what I would like to do in this presentation is to share some of the recent advances of the European Spintronics task force of the graphene flagship, which is exploring the potential of two-dimensional material for spintronic application. So I will not be in 30 minutes, I will not be able to give a complete overview of our activities, but I hope I can give some flavor of it, okay? So first of all, okay, it doesn't, let's see, I cannot, okay. So I'm located in I work at the ICN2, which is a core institute of the Barcelona Institute of Science and Technology in Barcelona, which is usually a lovely place to work in, but now our activity is quite reduced. And I'm leading a group which is developing predictive modeling for understanding quantum transport in complex materials. And for the past 10 years, I have been strongly involved in the graphene flagship. So the story started officially in 2013. The European Commission decided to launch an unprecedented instrument and funding scheme in order to accelerate the transfer of knowledge towards industrial application. And the graphene flagship was one of the two selected projects together with the human brain. Okay, so our mission was really to take graphene and related the layered materials from our academic laboratory to the technology, to the society, and hopefully revolutionize some industries and participate to job creation and economic activity in Europe. Our community was fortunate because Albert Fert was very enthusiastic and very supportive, and thanks to his efforts, we could have a fully dedicated work package focusing on spintronic and the potential of 2D material. So that's really, I thank him again, because he has been key for this activity to be represented. Actually, Albert and his group, just 1 year before the launch of the flagship, reported on unrivaled spin diffusion lengths in epitaxial graphene, which was outperforming any existing known material. So that was really a push towards exploring further what we could do with graphene and all related material. So 7 years after, I have actually the privilege and honor to lead the European task force, which includes key of the academic players of the fields, together with various companies which are actually working today on the integration of large-scale two-dimensional materials into spintronic technologies. In 2015, we actually published a roadmap for the 10 years to come, and actually our progress has been quite following the track that we publish in this review. And somehow, what we realize is really that now we have, in 2021, we are really close to this phase where, let me just put the pointer, this phase where we have to move really forward the fab environment. Okay, so I would like to show in a kind of visual summary what has been our strategy during those years. First of all, we devoted a lot of time in fabricating, characterizing, and optimizing technology building blocks at the laboratory scales, okay, with the main mission to work on the co-integration of 2D and magnetic materials, and also to demonstrate some kind of new paradigm for active spintronic devices. But during the recent years, thanks to the engagement of IMEC and companies like Nanosc, Singulus Technology, and Graphenea, more efforts have been devoted to moving in TRL, technology resistant level, and then move from lab to fab, mainly targeting the integration of 2D material in advanced memory technologies. So early on, I mean, graphene, and Albert anticipate that, was really envisioned to be an ideal materials for transporting spin information. For the following reasons: it was a material with a very low spin orbit coupling, and also a very long mean-free path or large mobility. So combining both, we were expecting actually that would be an ideal platform for moving electrons and spin information. So at the same time, being just a surface, it was also clear that maybe we could enrich the property of graphene and make him magnetic somehow, or spin active, just by very weak proximity effect. And this turned out to be one of the major aspects and interest of this two-dimensional material. So the consortium has demonstrated using high-quality exfoliated graphene and a different type of optimization at the level of the single device fabrication, somehow found the upper limit of the spin diffusion lengths. Here we have some of our partners' publication where they reported spin diffusion lengths up to 30 micron at room temperature. But the point is that in order to move to technology and application, we had to really focus on a scalable graphene and scalable two-dimensional material. Actually, CVD grown graphene and 2D materials are the one which are essential, not only for Spintronics, but for all kind of high technology which are related to photonics, electronics, medical techs, and so on and so forth. So really, CVD graphene has been one of our major targets during the past 5 years. Actually, just a few months ago, the European Commission, in partnership with the Graphene Flagship, launched the first stage of the experimental pilot line, which has the mission to really develop a process in order to enable very large volume production of electronic devices, and somehow to help manufacturing and scale up the production of these two-dimensional based devices towards the market. So this is a very important step in moving to ITRL, and also to really bring those materials to real product in the medium term. But those materials, those CVD grown two-dimensional materials, are not as clean as the one we know. They have this polycrystalline structure with a lot of defects and grain boundaries. And this was actually one of our major concerns, to which extent these morphologies could impact on the spin diffusion lengths, on the upper limit of spin transfer information. So we had specific activity during the past years. One was to try to anticipate by developing modeling on that. So we elaborate a realistic model of polycrystalline graphene. We worked also on trying to model all this disorder structure will impact on the energetics, including the spin orbit coupling impact from the substrate. And we also developed methodology in order to track the spin dynamics of electrons moving in these materials. Here it's an example where we inject some electrons in the center of the sample with an out-of-plane spin polarization, and then it propagates in this polycrystalline sample with an additional effect of the in-plane Rajba due to the substrate. And by looking at dynamics, we are able to extract the spin relaxation time, the spin transport length scale. And it turned out by doing this type of modeling, we were able to determine that there is actually a kind of universal spin diffusion length. It does not really depend on the average grain size of this polycrystalline sample, but it's completely driven by the strength of the spin orbit coupling induced by the substrate. And as a result, we could determine an upper limit for polycrystalline graphene deposit on the silicon oxide, which is 10 micron, and for polycrystalline graphene deposited on boron nitride, we can go to 50 micron, just because the spin orbit coupling is decreased thanks to the flatness of boron nitride. In parallel, there were efforts in the consortium in order to really work and study systematically polycrystalline graphene, spin transport. And in this work by IMEC and ICN2, there were analysis of many devices, and at the end, they were able to characterize the upper limit, which turns out to correspond to the simulation 2, which is in the order of 10 micron at room temperature, even though you see that the mobility of this graphene is not as good as the very high quality exfoliated graphene sample. But anyhow, this value of spin diffusion lengths are really very good for moving forward into our objectives. Very recently, there is still a debate about the explanation, but our colleague at Aachen University succeed in encapsulating graphene not only with boron nitride, but also with a strong spin orbit coupling material, tungsten diselenide, and they found an unprecedented mobility, reaching values never seen before, even larger than what the acoustic phonon limit would predict theoretically. So here we have something very interesting, still under analysis. But one clear question is, what about the spin characteristic in a device where electrons flow in a ballistic fashion throughout the device? So this is something that we had to analyze, and especially from the simulation point of view. We developed a methodology at ICN2 together with CEA, and we were about to make the first simulation of the non-local transport characteristics, and especially here with an external magnetic field, so-called Hanle spin precession, and we were able to investigate the transition from a dirty sample to a super clean sample where electronic transport, electronic mean free pass is much larger than the channel length, for instance. So we made a lot of progress, and this will help probably the interpretation of future Hanle spin precision measurements in ballistic devices. Now we have, of course, the capability with these so long spin diffusion lengths to start working on very complex architecture. This is an example of our colleague from Chalmers, Roche Dash, where he demonstrated that the non-local spin signal can be detected in different branches, and you can start to play at will by using lithography, and so you can start to make some kind of complex spin information analysis because we have this so long spin diffusion length. So now, beyond transporting spin information, we want to manipulate this information. We want active device. And as you know, this data spin transistor using an electric field was the first proposal, which has been difficult to implement. There have been more recent proposal and discovery with the spin Hall effect, where in absence of magnetic field, just because of the strength of spin orbit coupling, you can actually create pure spin current. And eventually this spin current can be used in a spin torque phenomena, so that you can transfer angular momentum to a magnetic materials, so that you can make this magnetization processing or reversing the magnetization. So this kind of spin manipulation, very interesting. Early on, Meir Beck-Chef from CEA pioneered the ab initio, the DFT simulation of all graphene deposit on magnetic insulator could gain some magnetic properties. He actually demonstrated that very giant exchange coupling will be generated by YIG. So YIG is a very interesting high temperature, high Curie temperature material. So this was in the 13. And recently, the combination of two-dimensional material, strong two-dimensional material like transition metal dichalcogenide, have shown really unprecedented properties that I will illustrate in the next slide. So in order to capture the physics of this van der Waals infrastructure, it is essential actually to have a very fine description using a DFT calculation about the effect of this interaction on the band structure, but also on the spin texture, because it turns out that spin texture will completely pilot all the spin property on graphene. The advantages of this interaction also is that, as you see here, calculation by the group of Jaroslav Fabian, the graphene bands remain located in the gap of this TMD. So you can avoid to have any transfer or absorption. You can also tune with the gate and absorb inside the bonds of the TMDs. But you have changed graphene. Graphene had become something different with a spin texture that it doesn't have otherwise. What we figure out is actually this specific imprinting of the spin orbit coupling into graphene will lead to a giant spin transport anisotropy. So here we just saw all the spin polarization change when you inject a charge with an out-of-plane spin polarization in graphene deposited on TMDs. You see that there will be a very large difference in terms of the relaxation between the in-plane spin injection or the out-of-plane spin injection. And we found that those values could reach several orders of magnitudes. At the same time, in parallel, our colleague from the consortium, Bart van Wees at the University of Groningen or Sergio Valenzuela, actually studied different types of van der Waals structure with TMDs, and they confirmed that this such a type of spin filtering effect could survive even to a very large temperature. In this work of Sergio, at room temperature, we get a factor of 10 or more difference in the spin lifetime. So as I said before, also there is a possibility with a gate to tune the spin transmission in graphene, and actually at some point you could get absorbed into the bonds of the TMDs where spin relax very fast. So somehow you can make a spin all electrical spin fed. This was demonstrated first by the group of Luis Hueso and Casanova in San Sebastian, and then within our consortium we also work on that at room temperature and show that the effect could be also observed at room temperature. So another phenomena that we were very interested in is the spin-Hall effect, which, as I say, is the creation of a pure spin current by using the strong spin-orbit coupling. Actually, after some controversies, one of the very important aspects is actually beyond the spin-Hall effect, is that we would like to have a material which has, at the same time, can transfer spin information over a very long scale, but this spin information can be controlled by an electric field, for instance. So this is kind of incompatible, because with the usual material, if you increase the spin orbit coupling of your material, even though the spin Hall angle, which manifests the strength and the efficiency of spin Hall effect, increase, then you will reduce the spin diffusion length. So this ratio, this product of these two important quantity is a very important figure of merit. And one of the main objectives of Spintronics is to move this up and try to find very good material for that. So this was the limit for conventional heavy metals. What happens last year, Sergio and Bart van Wees also, they reported unambiguous nature of spin Hall effect in van der Waals heterostructure. Using the imprinting of spin orbit coupling from TMDs on graphene, they could get at room temperature a figure of merit with which one order of magnitudes or two order of magnitudes from the conventional material. So this has been a very important achievement, because then we can start to use pure spin current into this complex architecture. So there have been also a very recent activity on this multi-layered transition metal dichalcogenide, such as molybdenum ditelluride or tungsten ditelluride here in the group by Roche. And they're also showing some very interesting spin transport property and spin active properties. There was a result last year in Singapore, which was very puzzling, because they not only report a very large spin Hall angle, but they also have estimated an enormous spin diffusion length in such strong spin orbit coupling material, resulting in a figure of merit which would be completely unprecedented. So we did the simulation in order to analyze those results, again with our non-local simulation, with some realistic modeling of the molybdenum ditelluride. What we found is actually because of some symmetry breaking in this material, there are multiple components from the spin Hall effect, and also the spin lifetime will depend on the injection direction of the spin. It turns out that the spin have a kind of constant spin texture in the YZ plane, which is something that is quite invariant in the Brillouin zone, and these provide very robust spin signal, as I will show. So here, actually, we extract from the length dependent of the non-local resistance, we could extract the spin diffusion length as a function of the energy, so in the range of several tens of nanometers. And then we could also investigate the spin accumulation and the spinel angle and compute the spinel angle, which we also found to be energy dependent and which is up to 80%, close to the bound age. And as a result, our figure of merit could get to this very, very large value, which is really unprecedented for Spintronics. So we have here a material which present extremely interesting aspect, very long or long spin diffusion lengths, together with very strong spinel angle. So it is one of the new material we wanted to have in our Spintronic toolbox. Okay, in this work, actually, we also propose, because not have been a non-ambiguous experimental evidence of the monolayer case. So we have in our analysis, our experimental colleague have reported the way to and the signature of such a kind of anomalous spinel effect in this TMD material by doing a Hanle spin precision measurements. I would like now to mention this work, because this work has been very fundamental. Again, a work by Meyerbeck-Scheff, which demonstrates that when you coat a magnetic material with graphene, what you change quite substantially the property of the magnetic material. And actually, what it turns out is that if you have this kind of coating in a memory building block, the result will be to reduce the current needed to switch the memory. Okay, so because there is a very strong enhancement of the PMA by this coating. So this was a theoretical prediction by Meyer, and with his colleague at CNRS, they also have some experimental evidence that that will be the case. But this has encouraged our partner IMEC to join our consortium in order to investigate to which extent the co-integration of graphene and related material into the current generation of STT-MRAM or SOT-MRAM could actually improve substantially the performances as it was predicted theoretically. So this is really, and IMEC, by the way, has been one of the first to report that it was possible to perform a 300 millimeter integration of SOT-MRAM for very low power ultra-fast embedded memory. So that was an achievement made by IMEC and Kevin Garello, who is the deputy leader of our work package. And so we have in Europe, this is a kind of illustration in Europe, we have been able to move from knowledge to almost to the fab environment and the integration into a real technology in a time of several years, and really like gaining a sort of leadership in that respect. So I want to mention this more recent two-dimensional magnetic material, because of course they offer an extra dimension for having even more compacted technology building blocks. And here, okay, this is one was picked up in 2018. Now there will be a talk just after mine, so very looking forward. It is clear that here we have a material which is really important for Spintronic. We are doing in a work package a lot of efforts. It's actually one of the main targets of our work, maybe more the fundamental technology building block at the moment, because this is a material that we don't know how to upscale like graphene or TMDs and things like that. But definitely there are a lot of very important aspects to investigate, to find materials that have a high temperature, Curie temperature, and also to have a control on the magnetism, and also to create van der Waals interest heterostructure, which could be functional, which just kind of picture like a kind of holy grail would be that at the end of the day we could pack but in an ultra compact fashion, several materials that will actually have all the capability to behave as an elementary and very nanoscale memory building block. So really, what I want to conclude is that we have been, I think, quite exciting by the progress during the past 7 years. Of course, this diversification of materials is a challenge in itself, because you have to find a way to tailor them, to fabricate device that will be robust and operational. You have the challenge of large scale growth, because of course there is the first step, which is doing all the single level device level to try to optimize, but then immediately we need to think about the possibility to wafer scale, and then also the connection with industries or with the fab environment is one essential aspect of this activity. So we are hopefully European Commission will continue sustain the efforts on this type of activity, so that we can keep a kind of momentum, and eventually we can have a very strong leadership in Europe in demonstrating novel materials in incorporating into this very advanced generation of memories. I think that should be almost done. So this was the conclusion, and thank you very much for this invitation, for your attention, and I'm happy to answer any question. Thank you.